Good afternoon. My name is Mike Joos, and I'm the Director of Business Development with T3 Global Strategies. We're a firm headquartered in Bridgeville, Pennsylvania, and we are a full services engineering, surveying, and geospatial services firm. And with me today is Marty Stoughton, who is a professional land surveyor with ESP Associates. They are headquartered in Fort Mill, South Carolina. Marty is based here in Pittsburgh, and they also are a full service engineering, surveying, and mapping firm. We're delighted to be a part of EnerGIS 2020, this all virtual conference. Excited to talk to you about a project that we performed for PennDOT back in 2019, a project that we think is absolutely fascinating. The title of our presentation today is Applying Geospatial Technologies and Data Fusion to Keep Miners Mining and Drivers Driving. And hopefully that's an interesting title. It caught your attention, and we appreciate you being with us here this afternoon. Before I get into the presentation, I do want to give special thanks to Rob Dean. Rob is the Assistant District Engineer for Maintenance with the Pennsylvania Department of Transportation, District 12, down in Uniontown, Pennsylvania. And as I mentioned, PennDOT was our client, and Rob was very much involved in this project and incredibly helpful in sharing some wonderful insight and some great pictures to help us put our presentation together. So special thanks to Rob for all of his help. Today, we're going to talk to you about the project itself, give you a little bit of context, what was going on, look at the folks who were involved in the project. From PennDOT's perspective, what was the challenge? What was the problem? What were they looking to solve? The solution that we put together, we're going to look at the technical approach and some of the cool technology that we used. And then finally, again, from PennDOT's perspective, did we solve the client's problem? So to give the project some context here, I'm going to borrow a term that a good friend of mine, Amy Lewis, who is one of the principals here at T3, is very fond of, and that's BLUF, bottom line up front. So just in a nutshell, in January of 2019, Alliance Coal planned to conduct longwall mining underneath a section of Interstate 70 in western Pennsylvania, which spans from the Claysville interchange in Washington County, Pennsylvania, across the state line about 1,000 feet into West Virginia. And with this longwall mining activity going on underneath the interstate, of course, PennDOT was expecting to see significant impacts to the roadway surface. If we look at the image in the upper or in the right-hand portion of our slide, if we look here, this is Interstate 70 coming down from the northeast and proceeding to the southwest here. It does, in fact, cross the West Virginia state line right here. And the shaded green areas are referred to longwall panels, and I'm going to touch on them in our next slide here, give you a little better understanding of what's happening there. So longwall mining, which is the principal method of extraction that the Alliance Coal uses in the Tunnel Ridge mine, they use these longwall panels, or they cut these longwall panels underground, and they're typically 12 to 1,400 feet wide, about 10,000 feet in length, and they are generally between 300 to 1,300 feet underground. As they are moving these panels, cutting that longwall face forward, they have hydraulic roof supports or shields in place to protect the miners. And as those shields, or rather as the longwall face advances, the shield moves along with it. So what happens is the roof in the mined out sections behind the shield begins to collapse as those shields are moved forward. And that's where we see the impacts on the surface then. Interstate 70 is a very heavily traveled U.S. interstate. If you're not familiar with it, runs east to west from just east of Baltimore, Maryland, through the Rocky Mountains and terminates in Cove Park, Utah. The annual average daily traffic, as I mentioned, very heavily traveled roadway, is about 34,000 vehicles a day for the particular stretch of highway that was involved in this project. The players at a very high level that were involved, the Pennsylvania Department of Transportation, District 12, again, they were our client. A gentleman by the name of Roy Painter was the PennDOT's technical advisor. They brought in the University of Pittsburgh as a research contractor. Their principal investigator was Dr. Anthony Iacone, We coordinated very closely with Dr. Iacone throughout this project. And then finally, Alliance Coal, who owns and operates the Tunnel Ridge Mine. A little background on the Tunnel Ridge Mine. This is one of several mines owned and operated by Alliance Coal. This particular mine is located near Wheeling, West Virginia. Longwall Mining, again, is their principal method of extracting coal to produce medium and high sulfur coal. This is a significant operation with annual production of 7.4 million tons in 2019, and they have estimated reserves at the end of the year 2019 of 71.6 million tons. So still a lot of mining to do here at this particular mine. The project timeline for panel 15, and that is the longwall panel that was going underneath I-70. They started panel 15 in November of 2018. They started under I-70 in January 2019, right around the beginning of the year. They finished under I-70 near the end of February 2019. So they were actually underneath the highway for about 2 months. And they did a full retreat where they bring all the equipment back out to the panel in May of 2019. PennDOT's objectives in this project, one of the reasons that they brought us on board for this was to investigate the influence of longwall mining on highway alignments and associated slopes and embankments. So not just the road surface, but the slopes and embankments also. They wanted to evaluate how the highway deforms during the undermining. They wanted to utilize models to better understand subsidence impacts to highway alignment and better determine how highway alignments could be impacted on future projects. So if you look at those last two bullets, you see that not only did they want to understand what was going on with this particular project, but they also wanted to have some really solid data to do predictive analysis on future projects, because while this is not an isolated situation, or it's not something that happens very often, rather, where mining is going underneath major interstates. It does happen from time to time. And in fact, it did happen here in Western Pennsylvania not all that long ago when longwall mining was conducted under I-79. Continuing with PennDOT's objectives, they also, and perhaps most importantly, wanted to keep the highway open to travel. And this is, to us, I think, one of the most fascinating aspects of this project. You think that stretch of highway, as I mentioned, 34,000 vehicles a day. They were expecting significant impacts to the roadway, but they wanted to keep the highway open to travel while this was going on. They also wanted to ensure the safety of the traveling public and then build the roadway back to the original design criteria. PennDOT's expectations going into the project was that they would see settling in the vertical axis of between 2 and 5 feet throughout the time frame that they were underneath their mining. Also looking for horizontal deformation from compression, pushing together, and tension, pulling apart. And another interesting aspect was that they would not see the impacts of the longwall mining for about 1 full day behind the longwall face, or about 150 feet behind the face. So as the face of the longwall panel was advanced forward, they would not see the effects of that on the surface for about 1 full day behind the face. So I thought that was kind of interesting as well. This image on the right-hand side is one of my favorites when you're looking at some of the impacts to the roadway and this vertical rule here. We often see signs on the highway that say bump, but we've probably never encountered anything like this. That's, it's easy to imagine that being well over a foot difference between the roadway surface and that roll. As you can well imagine, this was news. It did not take a lot of digging on Google before we were finding all kind of newspaper articles and new television news stories, rather. And it was news not only because of the impacts to traffic and people's commutes and all those kind of things, but just simply because of what was going on, the project itself, that there was major mining activity going on underneath this very heavily traveled interstate. Some of the roadway disruptions, this is what was going on. This is what we were seeing on the surface. And this was happening, pretty much 24/7. And PennDOT was out there. You can see the traffic in the background, but they were out there 24/7 making real-time repairs to the roadway to keep that highway open. Again, that vertical roll on the left-hand side. On the right side of the image, we can see some horizontal, and in this case, separation of almost 3 inches. Up on the right-hand side, we see some longitudinal cracking. Down here in the lower left-hand portion of the image, again, as I said, the disruption was not only to the roadway surface, but also to the slopes and embankments. You can see a culvert pretty much destroyed here. You can see difference in elevation from this section pavement to the next. Over here, we can see cracking across the travel lane here in the berm, and of course, some very significant settling here in this image right here in the upper right-hand corner. So again, the roadway was being severely disrupted. PennDOT was out there taking care of these issues in real time, keeping that highway open to traffic. Pretty amazing. Our technical approach to the project was really driven by PennDOT's determination that mobile LiDAR technology blended with field surveys and photogrammetry from aerial imagery. So there's the data fusion part of this, is blending those different data sets to deliver the desired solution. But they determined that that was the preferred solution to meet project objectives in terms of data robustness and the required accuracies for the analysis of the impacts of the longwall mining under the interstate to highway alignment, slopes, and embankments. So with that in mind, we developed this technical approach, and just taking a quick look at it here, we established a primary control network that included benchmarks that at the time, and Marty's going to talk about this here in a couple seconds, at the time we thought were outside the project area. We also established project control for the aerial imagery and mobile LiDAR. We acquired aerial imagery from manned aircraft at a ground sample distance, GSD of 4 centimeters. That's very high resolution, high quality aerial imagery, and combined that data with the initial mobile LiDAR run to create a project baseline. We performed 9 mobile LiDAR runs over a period of 2 months, performed feature extraction and photogrammetry on the initial baseline and subsequent mobile LiDAR runs, and then finally flew the project again when mining operations were complete to compile mapping for design of final roadway repair to bring it back to original design criteria. At this point, I'm going to ask Marty to jump in and talk a little bit more about the technical aspects of the project.
Well, as Mike was talking about, on these monitoring projects, you don't normally want to use control within the limits of the possible disturbance. And on this project, the primary control was run from National Geodetic Survey monuments that were in the vicinity, but outside of the supposed area of impact. But during the course of the project, it was determined that some of those monuments were impacted by the mining too. And we used US State Plane NAD 83 coordinates in the Pennsylvania South Zone and NAVD 88 elevations for the control of the project. And each time that we ran the mobile LiDAR system, the control was surveyed using static GPS procedures, and the digital levels were run from the primary control network. And we originally used the 32 targets for the baseline aerial and mobile collections, and the network had to be modified during the course of the project because of that road construction that Mike was showing you, and areas of major deviation that we needed to add some additional control there too. But originally we were required to scan within 24 hours of the control being run. But once that mining started, we quickly noticed that the need to start scanning as the control was being run, because that site was actually changing very rapidly. And we were talking about some of the area, you could see a couple tenths of difference within an hour's time. But on here, the summary results that you see on the page, that was from the original baseline scanning. And if you look at that overall RMSE value, that's very tight data that we were collecting out here. Next slide, Pibble. But these mobile LiDAR systems have been used in surveying for more than a decade. And most of our survey equipment manufacturers now are offering these systems. And I'm talking about like Topcon, Leica, Trimble, and Regal, just to name a few of them. And there's a number of configurations with single or double laser sensors, different cameras, and other add-on components, depending on what the project needs are. And we use the Regal VMX 1HA for this project. It's a dual sensor system with the Ladybug setup that you see there and 5 megapixel cameras, and then the 4 planar cameras that you also see. But as you can see from these photos, we use this system nationwide on a variety of different types of projects in various temperature environments. And believe me, it was very cold during the duration of this project, but it worked smoothly. Next slide, please. But the components from these systems have been around since the 1960s, and the early positioning systems, similar to what GPS is now, track ballistic missile locations around the world, and lasers measured the distance to the moon in the 1960s very accurately. After the Apollo moon landings, they left some reflective equipment up there, and they got really tight distance from the Earth to the moon. But the heart and soul of this system is the measuring head with the GPS and IMU. That inertial measurement unit is made up of accelerometers and gyros that update positions over 200 times a second. So we're getting really tight data. But we also, in conjunction with the camera systems that come with the system, again, we use the Ladybug to go with those planar cameras. And all those images are registered to the point cloud you collect, and they can be used to colorize the data if it's needed. Next slide, please. But the data was collected about once a week, as Mike said. We did a total of 9 runs out here in January and February. And the system, it collects over 1 million points a second. So it creates a very dense point cloud. And you can see those pictures there. They look like they're pictures again, but it's actually the intensity value, and every pixel that's on there has X, Y, Z data associated with it. So even the leaves you could pick at that time, any signs or things of that nature. But the data was registered and processed to the control, and then the data was cleaned and classified and readied for the mapping and extraction. And that photo on the left there, it's showing the DTM and the contours under the LiDAR data that was collected. But PennDOT did a great job of keeping the road surface clear for the scanning, because these systems don't really work well when the pavement's wet or snowy. Next slide, please. But just some of our project deliverables. Again, you know, the microstation DGN file was at PennDOT specs and standards, and the DTM was created with En-ROADS. But we delivered heat maps with each of those mobile LiDAR runs, and we generated those comparison maps also. But the LiDAR point cloud data was provided in LAST format, and the digital orthos were delivered at 1/4 foot resolution. Next slide. But just showing some of the data comparison, and this is actually like change detection techniques that we're using here. And that magenta or fuchsia, depending on what color that you see, is where the data moved the most out there. And we're going to see here in just a second, but next slide. And this is really telling that between drive 1 and drive 6, that roadway surface moved over 5 foot. And that's a lot of data. You wouldn't see it. You could see the stuff that Mike was showing those pictures of earlier with the kind of destruction that was happening. But when the whole roadway surface dropped, you couldn't see it with your naked eye, but you definitely see it in the data. Next slide, please. And this is an example of the CAD deliverables that were given from the aerial and mobile. This is the line work that we created. Next slide. And Mike was talking about the the monitoring of those slopes too. And that's what all these posts were put in for, to help monitor that side slopes, because some of this you'll see just a little bit you couldn't actually see with the mobile LiDAR. But the line work, the DTM, this is what was generated to create a surface for the engineers to design their new road surface. Next slide.
Okay, I'm going to jump back in here. You know, when we were outlining our presentation, we said that we would wrap up with the results. Did we solve the client's problem? And so this is from PennDOT's perspective. This is what they told us after the project. So first off, the roadway behaved as expected during the longwall mining operations with regard to movement in the vertical. So pretty much did what they were expecting it to do. The horizontal shift, or what they call the wave, was a little more difficult to measure. And in conversation with the University of Pittsburgh, they determined that further experimentation would be conducted to better understand those impacts on future projects. So, you know, that's kind of interesting, is even with that incredibly dense data set that the mobile LiDAR was giving us, they still found it just a little bit difficult to measure in the horizontal wave. The technical approach to monitoring the roadway during the 2-month period delivered the desired results. And then finally, based on the delivered mapping, the roadway was in fact built back to the original design criteria during the summer of 2019. So in essence, PennDOT told us that the project, everything went as planned. Our deliverables supported their applications, met their expectations, and they were very satisfied with the approach. Just a couple of images of the roadway being built back to the original design criteria, not only the roadway surface, but the slopes and embankments, all those kind of things, any kind of infrastructure, everything being put back the way it should be. And I want to share just a couple of quick videos with you. Full disclosure, these are not the I-70 project. This is in fact a project up near Scranton, Pennsylvania, Interstate 81 and 360, the interchange there. We did this for PennDOT, delivered it just a couple of weeks ago. Marty and his company collected all the mobile LiDAR for us. We did all the feature extraction and the photogrammetry. This is an example of the mobile LiDAR technology, feature extraction, data fusion, blending that with a photogrammetric data set, and just kind of give you some idea of what that looks like. From the mobile LiDAR, our focus was to collect from road shoulder to road shoulder. So anything off of the shoulder, any kind of infrastructure, any kind of light poles, utilities, all those kind of things, we did not collect from the mobile LiDAR data. We did not extract that data from that. Everything outside of that within the right-of-way was collected through photogrammetry from aerial photography. All of the vector data collected from the mobile LiDAR is also brake line data to support the DTM. You can see bridge decks there, catch basins, all those kind of things. Now we're blending the photogrammetric data as well. All of this is done to PennDOT specs. And Marty, if you have any comments on this, please feel free to jump in.
Well, these applications for what you were talking about, the assets also, we were talking with GIS applications, that we do a whole lot of asset collection and inventories for GIS systems with mobile LiDAR.
One more short video, just give you a different perspective. And this gives you an idea to the imagery that's being captured by the mobile LiDAR system. Let's see the vector data capture top and bottom of curb, paint striping, all those kind of things. So an awful lot of capability from these systems. Seeing it in profile now with the top, bottom of curb. And with that, we'll wrap things up. We are available for any questions that you might have. Look forward to your questions and comments. If you'd like to learn more about this project or our services offline, you can feel free to reach out to me at mjoos@t3gs.com or to Marty at mstoughton@espassociates.com. So thank you so much for your time, and we're available for your questions.